Don't say that, Brian. That's terrible.
Yeah.
How dare you swear, Brian? All right. So, for us today, big formulas notes. The 4 formulas we had from last week, the upgraded ones, the ones that are right, as well as this one, will be very beneficial for today. Any one of them can be used in any problem, so make sure you know all of them. Next, let's start at number 62. A CD has a diameter of 120 millimeters. When playing audio, the angular speed varies. Keep the linear speed constant when the disc is being read. When the reading along the outer edge of the disc, this angular speed is about 2,000 RPMs. Find the linear speed. A lot of times when you look at a word problem in mathematics, a lot of it is fluff. There are some crucial bits here that help you clarify some things, so I want to point some of those out.
Did we do this thing today? The daily question?
No, we don't. I figure I'd do them like every other day if I can. Okay, one point on a couple things here. Oh, that's great. That's beautiful. Okay, we're going to go with it. First of all, it mentions a diameter, which is pretty nice, because that, while it's not one of the pieces we need for the formula, we can use it to get to part of it. Second thing it mentions is it's along the outer edge. This is actually more important than you might think. Because if it's not on the outer edge, we need a different number. If it's somewhere on the inside, we'd have to have a different value than 120 millimeters. So the fact that it includes that information is actually very necessary for this problem. The rest of it, this piece right here, 200 revolutions per minute. It should be remembered, this is an angular speed. So that means that it is omega. 200 revolutions per minute. We have an R that is 100, or sorry, we have a D, a diameter, that is 120 millimeters.
And half of that would be 60.
60. Why do we need half that, Remy?
Because the radius is only half the way across.
That's right. It's one of those big brain things we need to have from geometry, is that relationship between the two. Now, in order to use this formula, I've added 2 little words up here to remind us this is constant, always the goal. In order to use the formula B equals omega R, which is the most common formula we have in our homework, 2 things are required. 1, omega has to be in radians. Omega could be in terms of degrees, radians, or revolutions. So if it's not in radians, you may have to make some adjustments to get it to be in radians specifically, which is why those little formula pages are so helpful. Second one, the radius, it has to be a radius. So that was why it was so good that everyone was able to put it in terms of a radius instead. So we're actually halfway done with this problem. We have R. So the last thing is, I want to get omega, but in the correct form. So let's talk about how to change this over. We have omega is equal to 200 revolutions per minute. I need to somehow convert this so it's in radians so I can actually use the formula correctly. I cannot use the formula unless it's in radians. It's not in radians, so I need to make a change. How do I convert radians into, how do I convert revolutions into radians?
1 revolution over 2 pi radians.
In this case, right numbers, you're upside down. The revolution is already on top, so I put it on bottom. And you said it was 2 pi radians?
Yes.
That's right. So a single spin around a circle is a single revolution. In radians, that's 2 pi. Which means, as soon as we make this conversion, the revolutions are going to disappear. Look at that, a disappearing revolution. France would be compressed. 200 times 2 pi would be 400 pi. Radian would be left on top because the revolution is canceled. Minute would be left on bottom. Before I convert this down into a decimal, I want to see, did it ask for it in a specific form? It just says find the linear speed. So the fact that it's a radian is the first half you need to make sure. It doesn't say anything about minutes or seconds or hours, so it's good. I'm going to go ahead and convert this into a decimal, though. 400 pi is equivalent to 1,200. $56? Mm-hmm. Yeah! I can do math. It's Tuesday. If it was Monday, it'd be harder.
It's not even a decimal.
I can't do the decimal. What's this one? 0.4?
6.37.
6.3? Oh, that was close. Color me impressed. All right. So now, we have an omega. We have a radius. If we want to find a linear speed formula states linear speed is equal to omega times r. So last step, I take v equal to our omega, 1,256.63 radians per minute, times our radius, which is 60 millimeters. Okay, I cannot multiply those two in my head. So 60 times 1256.63. I can't do it. I can't do it. What is it?
$75,397.8.
Okay, let's talk about the unit. Radian is a unitless measurement, meaning radian times millimeter will be just millimeter. Minute is a minute. So this is 75,397.8 millimeters per minute. It did not request it in a specific form, like meters per second or something random. So it just said find linear speed. We've done that. The problem is over. Note the tricks to these kinds of problems. We have to have omega in the right form to use this formula. We have to have r to use this formula. And so the most common thing is to make sure to fix one or both of them as we did in this problem. So that is number 62. 63?
Yep.
Very similar. Do we do 63 already? Beautiful. Okay. 63, for people that are at home. It's very similar, just with different numbers. Instead of 200 RPMs, 63 says 4,800 RPMs. So it's a very similar problem with just a different omega. So do the same conversion, and then make sure to use the same thing when it comes to diameter, and you will get the correct answer. Okay. All right. 64 and 65 and 66 are real fun.
Wait, 63 was like 62.
Exactly like 62, just with one number change.
Okay, 1, 2, 3.
All right, let me erase, and let's talk about 64. Okay. Having already done this problem once, I know I will not need the formula on the board, but without knowing that information, let's talk about 64, because it looks like it's trickier than it actually is. So let's talk about some things here. First, a person is standing on the equator of Earth, a radius of 3960 miles. What are his linear and angular speeds? Now, we have a formula, V equals omega r, that compares linear and angular speeds to each other. If we're given one, we can use it to find the other very nicely. If we're trying to find both, that is not the correct formula to start the problem with. I'm going to instead use the two formulas that we posted the other day. So those two formulas, the first one was the omega, the angular speed. So angular speed.
Omega equals time, equals angle over time.
Angle over time. So theta over t. Okay, before I start this problem, I'm going to go ahead and get the other formula down too, which says linear is equal to?
Yes, linear is equal to arc length over time.
So big S over t. Now, S is also a formula. Do you have that on the formula page?
Yes, it is S equals angle times radius.
So I'm going to use one of these two to get the final solution on that one. So these are the formulas I need to use. Now, a couple things to note here. Number one, they've given me a radius. So I'm going to mark that information down over here. So I have one of the three components I need over here. The radius is equal to 3960 miles. However, in the problem, they have not told me a time. They have not told me a theta. This looks like a major, major, major problem. It turns out it's only a major problem if you're not thinking realistically. The Earth moves in a very predictable way. Every 24 hours, what happens? So every 24 hours, so T is 24 hours, it changes one revolution. So my theta would be one revolution. We can also write theta in two other ways. Because it is a single revolution every 24 hours, it is also 360 degrees
And 2 pi.
and 2 pi. This is known. It is known. We don't need the problem to tell us this, although it would have been nice if it had reminded us that that's true. Okay, we know this. If this asks us about what was happening on like Venus or something, It probably would have had to tell us. But on this particular problem, it's assumed that you can look at this and go, oh, every day, that's 24 hours, it makes 1 revolution, or 2 pi / 360. Now, with this information, I have all the things I need to fill out the angular speed and the linear speed, but I want to talk about a couple things. Number one, to do the linear speed, I have theta r over t. I'm going to want to use the 2 pi. For this one, I need to use the 2 pi to get the answer to work out correctly. For this one, I actually have a lot of options. I could do any of these three, because angular speed can be written in any of those 3 forms, either revolutions or degrees or radians. One last thing, we were nice enough to say every 24 hours. That is not all we could say. We could say every 1 day. Because they haven't specified in the problem the time we're supposed to use. We could say, instead of 24 hours, we could put 1 day, and then our omega omega would have a different value for time. It would have days instead of hours. You can also do it in terms of minutes. There are 720 minutes every single day. We could do that instead. So we could do every day is 24 hours, is 720 minutes. So we could do time is 720 minutes for 1 revolution. Or 720 minutes for 2 pi. Or 720 minutes for 360 degrees. There's actually a lot of different ways we can write this depending on which form you want to go with. You could also go with 14,400 seconds if you really wanted to be crazy. But you need to pick one of these to work with. In theory, if you wanted to get really crazy, you could say every 365 days you make 365 revolutions. So you could do it in years too if you wanted to. You just have to make sure to pick a theta and a time that makes sense with how you're applying the problem. I'm going to do this in hours, specifically because of what happens out here. Let's go ahead and take a look. So for omega, I would do theta over t. I'm going to showcase the 3 answers you could probably get. You could get 1 revolution per 24 hours. That is one acceptable answer. 1 revolution per 24 hours. You can also get, 2 pi per 24 hours, which we reduce to pi over 12. You can also get, 360 degrees over 24 hours. Squeaky. All 3 of these are considered correct solutions, just in different forms, like Fahrenheit versus Celsius. They're just different versions of the same answer. 1 in revolution, 1 in radians, 1 in degrees. For linear speed, I need to use specifically the radian one, because the formulas work out. They need the radians to work properly.
Does the last one simplify?
Yes, it does. 360 over 24 would be 15 degrees per hour, I think. Hold on, let me check.
Yeah.
It is? Thank you. So this one simplifies to pi over 12, so pi radians per 12 hours. This one becomes 15 degrees per hour.
And those are all answers?
Those are all correct answers, because they're just different versions. And you can add more, because you could do, instead of hours, you could do minutes, or seconds, or years. You just have different versions of these same problems.
So pi over 12 will be answer?
Is one version of it, yes. Personally, it's the one I put. I put this one, because I work entirely in radians, when possible. So that's the one I picked for myself. But if you have any of those ones, or any of the alternatives, as long as it's correct, I will accept it. Let's talk about this bottom one now. This bottom one, when we choose theta, we have to choose the radian theta. Otherwise, the math doesn't work out. So, to fix this one, I'm going to choose to use this version of the formula with with theta and r instead of s, because it's the same thing. So I plug in. My theta would be 2 pi. My radius would be 3960 miles, all over 24 hours. So remember, this is 2 pi radians, but radians is a unitless measurement, meaning when you take radians times miles, you end up with just miles. On bottom, we end up with just hours. This is why I chose to use the hour one. It's because when I get to the velocity, I end up with miles per hour, which I have a good idea of what that is. I drive a car a lot, so I know miles per hour. It's very comfortable for me to know that. So I take 2 pi times 3960 all over 24. That is a decimal. It's not a ninth decimal.
No.
It is 1,076.
Yep.
Am I close?
36.
1,036?
0.73.
0.73? Okay. So this is our second solution, finding the linear speed. To put this in context, this means that if you are standing on the equator of planet Earth, while you are standing there, you don't feel like you're moving because it's a relative speed. But in terms of actual universal movement, you are traveling 1,036 miles per hour. Which is pretty cool. We can't tell because we're attached to it, so we don't notice the movement. It's the same way if you're inside a car and the car is traveling 70, you're inside it, you feel like you're not moving. Unless you have to accelerate or slow down. Say what?
How fast does a rocket go when it goes?
Escape velocity, it should be 579. No, it's much higher than that. No, 5,079
Miles per hour.
miles per hour. I think.
Technically, when you're in your car doing 70, that adds to that, correct?
Yeah. So if you're going 70 miles per hour on the highway on the equator, you're either going with it, so you're going like 1,100, because you'd be adding to it. You're going against it, and so the time gets lower. How many guys have actually flown in a plane before?
What?
Have you flown in a plane before? Okay. If you go in a fast enough plane, a cool phenomenon can happen. The time around you won't change if you go fast enough. Like if it's noon right now and you take off in a plane, if it's going fast enough, when you land, it will still be noon. Because of how the time zones work, right? So what can happen is if your plane travels at this speed in the opposite direction, according to the Earth, the plane is staying still and the Earth is just kind of spinning underneath it. But from the plane, it's the opposite. The plane is sitting still and the Earth is
You have to
going.
go in the speed of the Earth for it to.
Yeah. And the cool thing is, if you go in the other direction, like time travels twice as fast. So like a 4-hour flight is an 8-hour time difference.
Oh yeah,
Just
that happened
pretty
when
cool.
we went to Vegas.
Same. We were there over the summer.
Cause our flight she scheduled at home. Our flight was at midnight to come home. I was ticked.
So you were sucking on somebody else's blood? What were we ticked? Boom! Roasted.
I was just mad at it. I didn't want to get up.
Okay. 65 and 66 are very similar, so we're going to go ahead and do at least 65, and if we need to, we can do 66 as well, but I want to make sure to get to 67. So 65. Find the distance along an arc on the surface of the Earth that subtends a central angle of 5 minutes, with 1 minute equal to 1/60th of a degree. The radius of Earth is, again, 3,960 miles. Okay, this sounds more complicated than it is. This is just a unit conversion problem with a different unit that we haven't seen before. So let's go ahead and take a look at this problem, and let's know what we have so far. I'm going to start this problem, as with many realistic problems. It might be good to draw a picture here. So that's my first step. My beautiful Earth. America. It's up there somewhere, okay? Subtend means to have an angle that is represented inside the center of the circle. So there's my subtended angle. So this is where theta is. It's this little angle inside of here.
What is that?
It says America.
America.
It's like America, but you've got the A.
Oh.
America.
More.
Okay. It says the radius of this thing is 3,960 miles.
We see.
And it says theta is 5 minutes. Now, this is not minutes like you would think minutes in terms of like time. This was a special way of writing angles developed specifically by the military.
Ooh.
It allows you to take complex decimal versions of an angle's location, Because think about it. Right here in Missouri, we are near the 41st parallel. We're actually 41.9371. Here in Anderson, that's a long, complex decimal. If you're trying to relay information, relaying a big, long decimal is not the best way to do it. So what they did was they did it in what's referred to as minute and second notation, which converts the decimals using 1/60ths, which makes kind of sense. A minute is 1/60th of an hour, and so you can convert every degree into so many minutes and so many seconds. It's just a different way of approaching it. Why they call it minutes and seconds, not something new? I honestly can't tell you. I would have called it something new, but I'm a math person. I like new variables. So, they've given us how to convert this information. We have to find a way to convert this into a radian. If I want to find arc length, remember, is the equation S equals theta R. To use theta, I need theta to be a radian. So I need to find some way to convert this 5 minutes into radians. Let's start there. We already have R, so that's done. Let's start with 5 minutes. So I have 5 minutes. According to this little problem, it states there's a conversion. 1 minute is equivalent to 1/60th of a degree.
Mark Center, you're needed in the office for checkout.
A minute is equivalent to 1/60th of a degree. That is a conversion, meaning I can make a fraction. I want the minute to be on the bottom so it can cancel with a minute on top. So 1 minute is equivalent to 1/60th of a degree. Which means 5 minutes as an angle, again, 5 minutes as an angle is equivalent to, I would take, so the minute and the minute are going to cancel, leaving just degrees. And then I would take 5 times 1/60 to get 5/60 degrees.
Which is 12.
Which is 1/12 degrees. So 5 minutes is 1/12 of a degree. Very, very small. It would be very difficult to draw this by hand. But remember, if you're dealing with something the size of a planet, small angle differences end up having big effects as you get towards the edge. And you'll see here, 1/12 of a degree is actually fairly large in terms of the size of the planet itself. So, we have it now in degrees. That's nice. We know degrees. We've seen degrees before. But to use the formula, we need it in radians. I'm going to have to do one more step. I have to take this 1/12 of a degree, 1/12 of a degree, I need to convert it into radians. Now we have a conversion. 180 degrees is equivalent to pi radians. I should now be able to get the degrees to cancel. I have 1 times pi on top, to end up with pi radians on top. On bottom, 12 times 180. 12 times 180 is 2,160. So this is a very, very, very tiny number. If you were to convert this into a decimal, you're talking small. Okay? Very, very small. But this is my radian. I have my radius. I have my radian. I can now plug into the formula. And as long as I have a calculator that can help me simplify, I am officially done with it. Let's do it. I plug in. My theta is pi over 2,160 times the radius, which is 3,960 miles. Keep in mind, this is a radian value. Remember, radian times another unit, the radian will disappear, leaving just miles behind, which makes sense because it's an arc length. It's a length. Length is miles. Pi over 2,160 times 3,960. I want to say it's like 5 point something. 5.87?
75. 5.76.
5.76. So think about this. 5 minutes is 1/12 of a degree, which is pi over 2160, so very, very small. 1/12 of a degree is 5 miles on the surface. So from here to Pineville Center is only 1/12 of a degree. It's pretty neat. It's because of how big the Earth is, So note this was just a conversion problem. We had to convert the minutes into degrees and degrees into radians, and then we could plug into the formula and the solution pops out. Number 66 is the exact same way with a different minute. 66 says, find the distance along an arc on the surface of the Earth that's completed by a central angle of 7 minutes. So how would that change this problem? Just put a 7 there. And then continue the rest of the math like normal. This one's simplified nicely into 1/12. 7/60 does not simplify very nicely, so it gets a little nasty on the way, but when the answer is a decimal, it pops right out just fine. Okay, let's talk 66. We got about 2 minutes left. I want to at least get the idea down. 67. 67.
What did you say when you changed the 5 minutes to 7 minutes?
Yes, right there. Sorry, I just erased it. Okay, let's talk this last one. This last one's annoying because it's right after the other ones, so it talks about minutes again, but it's not the minutes of the Earth, it's minutes, actual minutes. Okay, if you haven't seen an analog clock in a long time, there's one on my wall. Look at it. Look at it. The question asks, consider a clock with an hour and a minute hand. We got one. What is the measure of the angle the minute hand traces in 20 minutes? So, I'm going to draw my very terrible clock. Clock?
4.
Okay, so here's 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Beautiful. Okay. You don't have to, but you have to get this to see it. Like, you have to get it. It's a weird problem if you're not thinking about it in this form. So, a question asks us, how far will the minute hand specifically travel in 20 minutes? So, I'm going to think of this as if the minute hand started up here at 0, or 12 o'clock. In 20 minutes, where's the minute hand going to end up?
4.
At the 4 over here. The question is asking, what's that angle?
More than 90.
It's more than 90. There actually is a nice way to get the solution here.
It's 120.
It is 120. How do we know it's 120?
Because it's 90 at the 3.
So
and then
here
you
makes
add
it
30
90.
to it.
Why would we add 30 to it?
Because it's 30 degree. As a unit circle, okay?
It just is.
Just is.
So there's a couple ways to approach this problem. One way. There are 12 numbers. A full circle is 360 degrees.
Correct.
So each number is a certain number of degrees. Think about this, right? The full circle all the way around. This starts at 0, ends at 360. So as you were correct in assuming, this is 90. That would make this 270.
Well,
That would make this,
did you try and say that I assumed?
180. Yeah, you did.
I did not assume. I knew.
Sure. Okay. You can see here that these numbers cut it into thirds. So this one would be at 30. This would be at 60. This would be at 90, which puts us at 120.
What I said.
That is one way to do it. Alternatively, instead of doing it that way, you could just look at it and go, okay,
Morgan Perryman, you're needed for checkout in the office. Morgan Perryman, office.
there are 12 numbers split amongst 360 degrees. So every one number is 30 degrees.
You didn't expect me to get it that quick, did you?
I am duly impressed, Remy.
Thank you.
Color Me Purple. Yeah. That's a great book. You guys should read it. Terrible play readings. Alright. That is the end of class.
I get to go sing English. Would you want me to be on my computer?
I get to do a test.
That's it.
He's